So, we already discussed about the stochastic process, stationary conditions, ergodic, and advantage of assuming the process to be ergodic, and we have estimated the first order statistical properties for a stochastic process, and we in the last class derived the connectivity between the load and the response, what we call as a transfer function. We already said that the variance of the response is actually a function of the white noise, which is a modified input of the modification of the input spectrum, which then depends essentially on a square d omega, and we already know that the response is a really narrow banded process for weakened damped system. For weakly damped system, response spectrum or response is narrow banded. It implies that it depends essentially on the transfer function, which depends on the ratio of omega omega bar and zeta, because transfer function is closely mapped to dynamic amplification factor, which is the ratio of the frequencies and the damping ratio in the given system. So, essentially this conveys me exactly the same meaning as that of a conventional dynamic analysis, where I do not bother about the statistical characteristics. I only bother about the input value in terms of its time history and try to find out the response either using modal response analysis, etc. I also have the similar meaning there, that the system response will be dependent essentially on the amplification factor of the system, which is a factor of the ratio of the frequencies and damping present in the system. I also got exactly the same meaning in terms of physical understanding, even through a stochastic process where we convey the same meaning, and we call this as white noise approximation, where the input spectrum is modified, because the variation of the input spectrum compared to that of transfer function is not very sensitive. So, we capture the sensitivity of the transfer function and keep it out of the integral, and this integral is from 0 to infinity, minus infinity plus infinity, and so on. This is what we have discussed. Now, we will talk about classical definition and understanding of return period. We already highlighted this partially in the first module, and we will recapture it again with the understanding of stochastic process. Then we will see how stochastic process can be useful for estimating the fatigue damage in a given system using linear approximation of cumulative damages. Let us talk about return period now, because period, the moment I say return period, people have confusion about the reference period and return period. A lot of confusions are there. Return period can be expressed in three manner. Okay, one on the time domain manner, one in terms of the risk associated with return period. The third could be a general definition of any value in a given set. Let Z be a random process. The random process, like we all understand, can be a wave height, can be wave period, can be stress value, can be bending moment, can be deflection, any value, let it be a random process, and I want to compare the value of Z of t with some of the threshold value small z, and I want to see what is the probability of exceedance of Z of t in a given set with that of small z. Okay, I want to see what is the probability of the value what I am observing in a given system exceeding any pre-assigned, prefixed, predetermined value small z. Okay, then I will call that as period of exceedance. Okay, that is what we call as return period. Period of exceedance. Okay. Let that probability P be probability of Z exceeding Z, which is given by 1 minus f capital Z of Z, that is a nomenclature. Z is the set of observation, Z is the threshold value with which you are comparing. Okay. Equation number 1. So, the probability of exceedance of the value observed by you, which is actually a random process, by comparing it with some standard reference value, because when you say exceedance you have to compare it with some value. Okay. That comparison value is a fixed value, and you are observing a set of values which is randomly distributed, and probability of that exceedance expressed by this relationship. Now, probability, or let us say exceedance of the observed value can be then stated as return period, which is R bar Z, okay, R bar Z, which is 1 over the probability of this value, which is 1 by 1 minus f z of z, equation 2. So, if you know this probability of exceedance, then you can easily find the return period, which is inverse of this, or inverse of this probability. Obviously, there is a very important factor here, which people generally associate this with return period. You have observed z set of values which is randomly distributed. Okay. Now, there is lot of uncertainty in recording z. You must know one important factor associated with return period is at what intervals you have got to record z, because the observation of z should be statistically independent. Okay. It should be statistically independent. So, to make any observation statistically independent, you have to have a sufficient delta t between the observations. Okay. So, if delta t is for delta t being the interval between the successive observations, over a period of observation t, it is important to ensure that the interval between the observations should be sufficiently large to make the observations statistically independent. So, in that case, the return period can be expressed. This is the second form of return period. The first form of return period is this. Return period can also be expressed by including delta t feature as given below. So, in this case we say that R of z, here it is R bar, here it is R, which is indicated as delta t of R bar of z. I call equation number 3. So, this is also called as return period, but this includes the feature of time interval between the observations. Now, we can also understand this with an example. Let us say in design of offshore structures, let us say the design load, which is also a variable, is considered as a probable value of exceedance of 10 power minus 2 every year. What does it mean? 99% the design load what to apply to the design will not exceed. Okay. 0.01, 1% it will exceed. Okay. That is in every year. Okay. So, there are two periods associated here. One, if we invert this, I get a probability, I get return period, because that is how we have got the return period in the first definition. Okay. The other period which is associated with this is this. Now, this is called reference period. okay, and probability of exceedance of this, which will give me the return period. In my case, it is going to be that okay, probability of the value, which is a variable, exceeding zeta is not the damping, zeta is some threshold value of the design load, which is going to be in my case 19% will not exceed. Now I have to define z. Z is actually a design load, this is a threshold value, where z is going to be the maximum of, because I have to consider the maximum combination of the given loads, which is considered as the maximum combination from the given set of load f of t for any instantaneous time within a given reference period of 1 year. Okay. So that is the condition. Therefore, r bar of z, hence the return period r bar of z, will be 1 over probability of z exceedance zeta, which is 0.01, going to be 100 years. So that is how we calculate the return period. Okay, it is going to be 100 years. That is a simple example to illustrate how we can compute the return period and what is the difference between a reference period and return period. Now we can also compute return period with terms of risk associated, because every load has got a risk. The moment I say the value will not exceed by 99%, now the counter question is, if we exceed by 1%, let us say the 1% exceedance is possible, what would be the level of risk if it exceeds? Because we are worried about the safety ultimately, and safety and risk are contemporary. Okay, so exceedance. So return period can also be expressed in terms of risk associated with the process. For example, let us take earthquake. This earthquake is a loading process, which is stochastic process. So there is something called design basis earthquake, maximum credible earthquake. There are two earthquakes which are used in the analysis: design basis earthquake, maximum credible is further redefined as considered also, maximum considered earthquake, but it is actually credible earthquake. Okay. Now they are given with respect to the risk associated. The design basis earthquake has got 10% risk occurring at 50 years, whereas the maximum credible earthquake has got 2% risk, or it is associated with 2% risk. What does it mean? So there is an input signal which you are going to consider for the design. If I want to call the input signal as a design basis earthquake signal, then it has got a probability of exceedance by 10% risk within 50 years. Whereas if you have a signal which I want to call or qualify as maximum credible earthquake, then the exceedance of that signal in my design life or in my given system is only 2%. Now I can compare these two and get back my return period on these two, like the equation here. For example, the risk associated is connected to the return period by a given expression, which is 1 minus 1 by t of n. So let us say risk is 10% here, that is 0.1, that is what I am looking for my DBE, design based earthquake. So 1 minus 1 over t, t is the return period I do not know, whereas the reference years is 50. Okay, if you calculate t, you get T as 475 years. Whereas when I substitute this risk as 0.02, on the other hand for MCE, then I will get T as 2500 years. So this will now give you a comparatively physical picture of understanding it is that earthquake which will be exceeded in its process, not in the system, in its process by only 2%, which will reoccur once in 2500 years. But the 25th 100 year can be this year also, where you are designing your platform. Okay? So you cannot say, since I am designing my platform today in 2015, my return period is 2500 years, therefore my service life is only 40 years or 30 years, let me not bother. It is not talking about the design life of the structure, it is the return of the process. We really do not know when last 2% expense occurred. So, but if it have occurred, if you know that, if you are alive during the time, you will be sure that 2500 years after only it will get returned. But since you do not know that, because the process is random, as I said, random process is value is fixed, you do not know the value, therefore it is random. So if it is random process, you do know the value, so that occurrence period can be this year where you have commissioned a platform, therefore risk is always there. Okay. So risk when associated with return period will give you fairly a practical meaning of understanding the connectivity between the return period and risk, where n is a reference here. It means return period cannot be quantified in a given design if you do not have a reference period. Okay? So do not try to give a reference period, return period without reference period, there is no meaning. Okay, this is how return period is generally qualified in stochastic process. The second one could be how this process can be used for fatigue damages. Now why we are bothered about fatigue damages? Fatigue is a process where the amplitude is not exceeded instantaneously, so there is no damage caused by excessive amplitude. The difficulty with fatigue is the amplitude is within the threshold value, but the number of cycles the material is subjected to has exceeded the threshold number. So the amplitude is very small, but you are doing that amplitude for n number of times. You are whispering on somebody's ear 1 million times a day, so he gets irritated. So that irritation is the fatigue damage. Whispering is a low decibel level, maybe 1 decibel or 2 decibel, you are not disturbing anybody, you are going and simply whispering on his ears about 3-4 million times in a day. So he gets irritated. So that is a damage caused to the ear, because the amplitude is so low, but the number of cycles what the ear can sustain the whispering is very high phenomenally, therefore you cannot sustain or the ear gets damaged or person gets impaired. So let us talk about fatigue damage. Fatigue damage can also be estimated using a stochastic process like this. Let us see how. Now fatigue damage is if a material essentially metallic, okay, composites, all these are not included in this. You should have the sustainability for reversal of loads. All material do not have this. Okay. Your friend should be able to listen to you 1 million times. If he closes his ear, no fatigue. Okay. So material should allow reversal of forces. Okay. So essentially metallic material unfortunately come with this inbuilt characteristic. Okay. So metallic materials is subjected to harmonic stress cycles. Why is it harmonic? Harmonic got trough and crust. Harmonic stress cycles. If a material subject to the harmonic stress cycles of a constant amplitude, which is larger than certain number of acceptable value. What otherwise we call threshold value. We can always say this as magnitude. Value does not make any meaning, because I am talking about the stress, I should talk about the amplitude. Now one can ask me a question, how will you decide what is the acceptable magnitude of stress value? This is material dependent. How can you compare this? For example, you are whispering on ears of A and ears of B. A can sustain 1 million cycle, B will not sustain even one more. Okay. The reaction of A and B to the same whispering decibel of the same number of cycles of the same amplitude is different, because material characteristic of A and B are different. So, material dependent. Can cause fatigue damage. Is exceeded, it can result in, so that is a statement, no? If a material value subject to harmonic is exceeded, it can result in fatigue damage. Interestingly, there is very fundamental characteristic about the fatigue damage, because people talk about let us say fracture mechanics, there they will talk about fatigue and fracture in detail. We are not touching about that, because we are doing fatigue discussion only for about 15 minutes. So, it is very difficult to qualify an understanding on fatigue damages and fatigue responses in just 15 minutes, but since I am interested to touch upon this topic, which is one of the important areas in stochastic process, touch upon this. Important character fatigue damage is the damage is always cumulative. It is irreversible and cumulative, that is the problem. Okay. Every fatigue damage has to be computed as a cumulative, because the fatigue damage being a low amplitude value, it does not demand irreversibility, because the damage does not occur actually. Okay. It is always cumulative, that is a very serious problem here, and most of the successful models where people use fatigue damage estimates are linear. Okay. I will talk about these 2 points now. So, one is the cumulative one. So, now let us say how to compute this is given by a simple relationship, which is n s power m is k. I call equation number 1, where m and k are constants depending upon the material and type of loading. M is usually 3 to 5 value, simple number. I am worried only about the material steel, so sorry, marine steel. Okay, it's 3 to 5. It's not for all material same number, it varies. N denotes the number of cycles to fracture. So, let us be very specific, number of stress cycles, we are talking about the stress magnitude here. Of course, as I said, you have to fix up a threshold value. Okay. So, S denotes the stress range. Okay, these are all stress symbol, do not write the 6, okay, it is stress value. Otherwise, you will read this as 6 range and etc. 6 cycles, you will completely confused. I think you are clear with this notation, stress. I am writing, avoid writing the word, I am writing the stress value. So, why we are talking about range in stochastic dynamics? You cannot always qualify an exceedance by a single number. Why? Because the whole process is random. Okay, you have to give a range. The moment I say a range, always as a range width or band. So, from that plus and minus. So, S minus A and plus A, the range is to A, that is how we fix up the range. Okay, it is always, it is the other way. If you say S plus 2A, no fatigue, fatigue is only reversal. So, you have a threshold value, plus and minus of that value is actually fatigue. Okay, if you have only one value inside, it is exceeding only, not coming down, no fatigue. Okay, so band is always plus and minus of half of the range. So, you get the range double of this value. So, yes, k minus this. This hypothesis was suggested by Palmgren Minor, called as Minor's rule. In fatigue estimates. Okay. This assumes the damage to remain linear. So, for a given loading history, so that is the important input you need. You may ask me why this input is required. If you do not have the loading history, you cannot calculate the threshold range of stress value, number 1. Number 2, from the loading history you will not know how many times it is exceeded and it is not exceeded. So, you have to have the history. The moment you talk about history, I must always have a period for a given loading history for a period T, because I cannot consider infinite history, okay, for a period T. Cumulative fatigue damage which is d tilde t is given by small nj by capital Nj, where small nj is the number of stress cycles in the time history associated within the stress range. We are not bothered about the value of stress values beyond the stress range, only in the stress range the number of cycles associated we are interested. This is not 6, this is again stress cycles associated. Capital Nj is the number of stress cycles leading to fracture, which is given by a simple expression which is k Sj to the power minus m. Okay, we got it from equation 1, I just reversed it. So, the cumulative damage or the damage is occurred when d tilde is 1. Okay. When it occurs, damage is caused. For d tilde equals 1. Now, one can ask a very interesting question, why fatigue damages are cumulative in nature? Why fatigue damage is cumulative? Why I should consider cumulative effect? Because when Nj, maybe one of the element of the capital J's, is more or less equal to the exceedance of stress value within the given range, it eats away the lifetime of the structure. Physical example, one cigar smoked has eaten away, for example, 30 seconds of your life. So, 2 cigars, already 130 is gone, the second cigar again 30 seconds. So, it is cumulative damage. Though smoking one cigar alone will not cause fatal, okay, stress exceedance is there, but it is within the threshold value. So, the reverse effect is not visualized by the human being. So, when you keep on smoking continuous cigarettes and you can say today I smoked only 5, the doctor would say you have smoked 3500 cigarettes earlier, therefore lung is spoiled. So, cumulative damage. Okay, the threshold value is exceeded cumulatively because it eats away the lifetime of the structure or the human being parallelly. Exactly, that is why the damage in fatigue is cumulative. So, let us take a stationary process x of t. Let x of t be a stationary process, because when we wrote this sentence for the first time in the stochastic dynamics class, we were worried that what is a stationary process, whether it is the same stationary as we get in Gurunath, we are worried about that. Now, we really know what we actually mean by a stationary process, because we have a lot of information about that. So, we know that stationary process and a zero mean process. I can add more complication to this because we all are expert in what is a zero mean process. Zero mean and narrow banded, all will happen because we already know all these things will happen in a given system process. Then the cumulative, actually literature uses a different word, they say accumulated, that is what the literature says. For me, I understand easily this word cumulative, okay. Accumulated damage d tilde t for this case will be given by over a stress range A, over a stress range A, it is a continuous variation n tilde A by threshold value N A d A, equation number 3. The denominator N A, where N A can be given by the equation which we already know, which is k the stress range to the power minus 1. Why I am putting 2a here? Because the stress value is n plus and minus a, I get 2a. Because in this equation I must put the full range, okay, 2a minus m, and m is a material property. Now the expected value, this is where I am moving to stochastics. The expected value, because always I am looking for a mean value. So the moment I say expected value of the damage is given by d of t, which is expected value of d tilde t which is expected value of NAD. Equation 4. Of course, this goes 0 to infinity, because mean is only the positive response of the system. Now here we are worried about the expected damage of this, which is n hat, which is actually the observed value. So this can be computed for a given von Mises stress failure. There are different kinds of stress theories available in the literature. Von Mises stress theory is one which is popularly used for fracture damage estimates. So we are talking about the expected value of n hat or n tilde of A, which is easily given by the multiplier of the response amplitude function and the power spectral density function, which we already had in the first lecture of stochastics. So I am replacing it with a different symbol. So Vx 0 t, they are not multipliers, they are actually one term, okay. Vx 0 of t, only the positive value, okay, Vx 0 t of that of f of xp a d. Where f of xp a d a or f of xp a is actually the relatives of the peaks with amplitude, is the relative peaks with amplitude, that p stands for that peak value in x, where x is at the stationary process, relative number of peaks, okay, relative number of peaks with amplitude a, and of course there is a range. So with amplitude a and a plus dA, increment in a, whereas Vx naught t is actually the total number of peaks which is equal to the number of cycles, because it is going to be same. You can either count the peak of exceedance or the number of times it has exceeded, it is one and the same actually. Okay? In a given value for count, either the threshold value exceeded or the number of times exceeded, it practically give the same number. Okay? Which is actually as same as the equal number of cycles exceeded within t, because we have to look at the window of capital T. Now d of t, now d of t can be given as, because I have E expression expected value of n of hat here, I can substitute this back. So this is going to be a constant total number. So V x0 t integral, because I have an integrated function, integral function there, which is fxpa 0 to infinity fxpa dA by n of a. And already we have an expression for Na. Okay, you can substitute that back here. Therefore, that will become Vx0 t 2am by k fxpa d. Now, for a narrow banded process, already we said that x of t is a stationary narrow banded process. For a narrow banded process, it is generally Gaussian distributed. Hence, for a Gaussian process, the power spectral density function fx of p a can be given by a standard expression available in the literature, which can be given by a by sigma x square, the variance, exponential with e power minus a square by 2 sigma x square. E power minus, okay. I call this is equation number, I mean I do not know if I have left 5 somewhere, there is going to be 6. So now substitute back this PSD on equation d of t and get d of t back. So d of t, now d of t will be given by, which is a cumulative damage estimate. I will write down the expression in short form, which is Vx0 plus t to minus sum. I am writing in a very specific format which is comfortable for me to explain later, k sigma x square integration 0 to infinity am plus 1. Now there is one a here, there is one 2m here, am plus 1 exponential or of this function, this is one and the same. Okay. Now this integral is a standard integral which is against a dA, which can be evaluated as a gamma function. Okay. So I write that value here, Vx naught t plus by, let us say k 2 root 2 sigma x, 2 root 2 sigma x to the power m gamma function 1 plus m by 2. M is a material property. Now for our understanding, we are very good engineers and mathematicians, gamma function of n, any variable n, or let us say be very specific, n plus 1, because we have a function here like this, is nothing but factorial n. For n equals, is it going to be 0? No, 0, 1, 2, that is a standard equation function available in the mathematics. Okay. So gamma n plus 1. So if I know the value of m, I can estimate this. Okay. Now, I will call C question number, let us say this is 7 and this is 8. One is actually not interested in estimating the damage or cumulative damage. Ultimately, if the structure is getting cumulatively damaged, if a person is smoking cigarette continuously, what is the lifetime of the person? So, lifetime estimate. Okay, the lifetime estimate. Because we know that to get the lifetime estimate, damage has occurred. So, I must say d of t is 1, damage has occurred. So, substituting d of t as 1 in equation 8 can be estimated by setting d of t as 1 in given equation 9. If I do that, I will get t, there is no bracket here, okay, t as k Vx0 inverse 2 sigma 2 2 root 2 sigma x m by the gamma function. So, I get the lifetime estimate, call equation number 9. So, one can get the lifetime estimate if you know this. Now, interestingly, it is very difficult for us to compute Vx0 for a given system. So, Vx0 can be in stochastic process comparable to 0 mean crossing period. Vx0 is comparable to 0 mean crossing period, which is known as Tz in the literature. Therefore, T is nothing but k Tz times equation 10. I get the lifetime estimate. So, I can use stochastic process to estimate fatigue damages also using the Miner's rule or using this kind of relationship, where I know all of them because I know the variation of the process, the standard deviation, I know the material characteristic. There is a material property again, type of loading, k is known to me. Tz is of course a count available from the stationary process, can easily find the lifetime estimate for this. So, it is very easy and a closed form solution which can give you the damage estimates using stochastic process. Okay. So, these lectures of 4 to 5 lectures in stochastic dynamics has made you to give an introduction to how dynamics can be done, even though people claim that the given input loading is not defined, it is not well prescribed, and people say the variation in wave heights are so high it cannot be considered random stationary process. Okay. There are arguments. They can be considered stationary process if you take long term statistics, okay, they can be called as a stationary process. So, there are arguments plus minus. So, stochastic dynamics is in the verge of let us say research application in offshore industry. Okay. So, we have completed all the 3 modules now. In the module 1 we talked about introduction dynamics, we moved on further from first degree to that of multi degree, we solved problems with 4 and 5 degrees here. Then in the second module we will apply the dynamics understanding to FSI, fluid structure interaction. We picked up various generic modules, then we picked up specific examples of offshore platforms, we derived the complete equation of motion terminologies, we discussed in length about the damping properties, different varieties of damping, and we did lot of numerical examples to understand structural dynamics in terms of fundamental applications and appreciation. Then we moved on to higher end understanding of dynamics using stochastic theories or stochastic process like this, which is also one of the methods of appreciating. We have discussed time domain solutions, we have discussed iterative frequency domain solution, we have discussed about the transfer function approach which can be used for frequency domain approaches, etc. So, we have got and we have discussed the Newmark's beta algorithm, we have solved examples and we have given research papers for a reference to read, and we have made a one-to-one correspondence of what has been published in the paper, what experiments have been done, what numerical studies have been established, how they are connected in new generated software structures at IIT Madras, where we did lot of experiments and new forms of offshore platforms which has been also told. Okay. So, we have got extensively a good understanding through this course on structural dynamics applied to ocean structures with various salient examples where we stand vertically special on certain areas of ocean structures where we conducted experiments and published literature, we have authenticity, we can say that yes, we are able to at least relate the fundamentals of dynamics to an application problem on offshore structures using this kind of analysis and systems. So, we also showed in between the classes and lectures that how design can be also sufficed using structural dynamics as an analysis tool. So, why dynamic analysis is important, how designers look dynamic analysis as a primary tool in the design stage itself, we have sufficed that also. So, it has got a very good let us say horizontality, and of course, in certain areas very great deep verticalities on certain subjects of interest. I think I am very confident that whatever lectures were given and turning back again and looking at this, and we have got about 2 books authored at IIT Madras on this area. There are many courses available, many textbooks available on structural dynamics, many authors have contributed, all of them equally important. We have referred more than 85 papers in the NPTEL website, all papers, all books, all notes, all will converge to a single understanding of enhancing confidence in dynamics. If that is the achievement what we are able to do at the end of the course, I think we have done our job. Okay? Thank you very much.